Good morning and thank you for coming. In the Mass Network Topology series, this week we had three. Okay, to follow the three of them, all excellent. Today we are very happy to have with us Alexandre Proutiere from the Regulation of Technology in Sweden. He studied in Ecole Normale Superieure Paris, and then in Ecole Normale Superieure, the Telecoms Paris. He got his PhD in applied mathematics from the Ecole Polytechnique in France. Then he worked in the France Telecoms for a number of years. Then he worked in the research department of Microsoft in Cambridge, where the best people in networking for Microsoft are. And then he joined Regulation of Technology, where he's now an associate professor. He has received many awards, including the ACM Sigmetrics Rising Star Award, and twice the Best Paper Award for ACM Sigmetrics, and once the ACM Mobihoc. And he was an associate editor for identity reception and networking of print system and applications, correct? You think that. Okay. So today he's going to talk to us about bandit optimization with large strategy sets and applications. Welcome.
Thank you. So thank you very much for the invitation, John. It's a pleasure to be here. Today my talk is about bandit optimization. It's a very old topic, but I hope I convince you that there are still interesting questions in this area. This is basically joint work with my postdoc, Richard Combs, who actually was the main contributor of this work. So I have to say big thank you to Richard. He's a very strong, gifted researcher. I borrow the title of my presentation. It's actually the same title as the PhD thesis of Robert Kleinberg. But I guess we have different kinds of results and new results. All right. So the outline of my talk is as follows. I'll give two examples to motivate bandit optimization and why I was at the first place interested in using bandit optimization techniques. In the second part, I will give you some background on bandit optimization. I will solve in the third part of the talk what we call graphically unimodal bandits, and then I will go back to the motivation and show how we solved the problems that initially motivated my work on bandit. So let's try to first motivate the use of bandit optimization techniques. So the first time I worked on bandit, it was to solve this very simple problem that engineers face when designing rate adaptation schemes. And one of the most important rate adaptation schemes that we are all used today is that implemented in Wi-Fi in AO2.11 systems. In such systems, so you imagine that you have a source that a lot of packets to send to a common receiver, to a receiver, and to send each packet, he has a choice between, let's say, a certain number of rates. So it depends on the standards. In AO2.11g, for example, you have 8 rates available, ranging from 6 megabit per second to 54 megabit per second. And of course, the rate you choose should be optimal in the sense that it should maximize the throughput, which is the rate times the successful transmission probability of the packet. Okay, this is the throughput. So the problem, of course, is that you know the rate at which you can send the packet, but you don't know the success probabilities, the corresponding success probability. And as a consequence, you don't know the throughput, the resulting throughput. So you start at time 0, and at time t, you want to have sent successfully the biggest amount of packet. Okay. So how should you optimally and sequentially select the various rates? Okay. So of course you don't know the theta, so you are going to learn them. And all the rate adaptation techniques that are used today are basically heuristics. They are based on no theoretical background or framework or nothing. So my idea was to bring back some of the tools of stochastic control and bandit optimization to actually solve this problem precisely, exactly. And I will show you that actually by doing that, we improve the performance by a huge factor, which is usually not the case in engineering, right? I mean, all my career, I was frustrated because I have strong mathematical background. I can apply mathematical tools to solve exactly and optimally problems. But as it turns out, often is that engineers, they are able, they have good intuition, and they are able actually to design systems that are close to optimal, even if they don't know it. Okay, but this is not one of these scenarios. Sorry? I will talk about varying theta later.
Can you assume independence from slot to slot?
Sorry?
You assume independence from slot to slot?
So it's an IIT process for a given packet. You have a success probability that drives your IIT process, and that's it. This corresponds more or less to a fading scenario where basically you would have relay fading. It's fast fading.
And what are you allowed to know as you as a designer of the system?
That's a very good question. I didn't mention that. In most of the wireless system, what you know is, for example, in LTE system, in cellular system, you have a lot of feedback, you have a lot of probing to know what's the channel condition between a transmitter and a receiver. Here in 802.11, the system is dumb in the sense that when you send a packet, you only get binary feedback, which is I received the packet or I didn't receive the packet. Measurement-based systems could be more efficient, but they require a huge overhead, especially for systems with a large number of subbands like OFDM systems. So as we go towards systems with more and more, using more and more frequencies, the problem of designing the right feedback is increasing. And it's one of the future direction I want to do. All right, so this was the G standard, and why I was interested in this problem is that in new standards, not only for each packet you have to choose a rate, but you have to choose what they call a MIMO mode. So basically, nowadays access points have several antennas, and you have to decide whether or not you should send the same information simultaneously through the two antennas, or if you should send independent information. So the idea, of course, is that when the receiver is close to the transmitter, you can use both antennas to transmit information that are not related with each other, because the receiver is close and can actually decode both information. When the receiver is further away from the transmitter, what you do is you try to exploit what they call spatial diversity, and you send the same packet on the two antennas, so that to strengthen the signal that is received, and so that it can decode. Okay. So as you see, the number of possibilities for sending a packet is increasing as standards are evolving, and actually, as of today, we have no clue. Before this talk, of course, we have no clue how to design MIMO mode and rate adaptation scheme. And there have been heuristics, and it's a very active field of research in wireless. Okay.
What is the diagram?
I will explain that later. Okay. It's a graph. Okay. The second application, it came from what they call adduction. So you are all very familiar with, unfortunately, with adductions, because you are bombarded by advertisements all the time. And what's happening is that, for example, in Google or in Bing, when you enter a query, basically before you have the organic answer of the search engine, you have sponsored links. Okay? And the way these links are chosen is based on an auction, but it's a weighted auction. The result of the auction is weighted by what they call the click-through rate. Okay, so basically, the result of the if you bid $1 to get advertised, if you are a company you want to bid $1, Google is going to multiply this bid by their estimated click-through rate to rank the different advertisers and to actually display them on the web page. Okay? And so one of the crucial component of this system is to actually estimate the click-through rate. Right? And the click-through rate is important. Why do they multiply by the click-through rate? Because Google is taking money from the companies only if the user that enter the query actually click on the link. Okay? So if you don't click, you have no revenue. So multiplying by the click-through rate makes sense from a revenue perspective. Right? So, but what you need is really to estimate the probability that the user, if you show her this advertisement, will click on it. And the current practice is rather, secret, of course, but I can tell you that generally people build huge graphical models in Bayesian framework and apply some kind of expectation propagation algorithms to estimate this click-through rate. Their underlying goal, of course, is to minimize the mean square error on the click-through rates. And the underlying assumption is that, well, these click-through rates are not evolving over time, and this is good enough. If you minimize the error on the click-through rate, then maybe it's good for your system. My motivation in studying this was to introduce dynamics in the systems. First of all, you have changing ads, the click-through rate are evolving over time, but most importantly, your goal is not to minimize the error you make on the click-through rates. Okay. But your goal is to maximize the profit, the revenue of the engine. So it's not the same thing. And it turns out that this is really a Bandit problem. So if you think about it for a while, you have a set of queries. Okay, the queries are a combination of users, of a user and a question. So for example, Armand is entering car insurance in the engine. Okay, this is one query. There are a huge number of queries. Okay, it's here I put 10 to the power 9. I have no clue actually, but I think it's much bigger than that. The number of ads can be huge as well, typically millions. Okay? And for each couple, you have a click-through rate mu ij. Okay? For query j and ad I. Okay? And this big stuff forms a click-through rate matrix. If you knew the click-through rate matrix exactly, you would be able to select the right ad, the ads that maximize the revenue of the engine. Unfortunately, you don't know it. You estimate it on the way. So your profit, your revenue after T queries is just the sum of the revenue. So here, don't pay attention too much to the formula, but BITJT is the bid, the winning bid of the bid of advertiser I of T when the query at time T is J of T. And XIT J of T is a random variable representing whether or not the user is going to click on the ad. And so it's some kind of online matrix completion problem. At some time T, you have observed a couple of entries of this matrix, actually realization of the corresponding random variable. This is binary observation. If you have a 0, it means that the corresponding query and the ad that was shown has not been clicked. If you have a 1, you get a click. So this is the picture you have. You have a query arriving at the engine. It's basically a column here. You basically select a subset of candidate advertisements, and among these this subset, you choose the one you like and you display it. And you receive or not a click. And here you don't receive. So you understand it's a Bandit problem. I will talk a bit more about this problem later. Okay. So let's turn to I'll give you a brief introduction to stochastic bandit optimization. There have been a lot of things that are termed bandit optimization. So here I talk just about stochastic bandit optimization. It means that the rewards that you observe are generated according to a stochastic process. So I guess bandit optimization problems are the most fundamental sequential decision problems with what we call exploration-exploitation trade-off. These problems were, as far as I know, introduced by Thomson in 1933 in the context of clinical trials. The problem he looked at is as follows. You have patients arriving at you, they have the same disease, and you have two available treatments. And each time there is a patient coming at you, you have to decide either to give the red treatment or to give the blue treatment. After you give the treatment, you observe if the patient is cured or not. What Thomson looked exactly at is the so-called one-arm bandit problem, which means that there is one treatment for which you know the probability of the success probability, the efficiency, the average efficiency of the treatment. So let's say you know the red treatment is effective 60% of the time, right? And you don't know the blue treatment. So the question is, the blue treatment is new, maybe it's better. It comes from the University of Maryland, and hundreds of researchers worked on it. Still, you want to test it against the red treatment. Okay. So how should you do it? Okay, and that's the question of that's the problem solved by Thomson. And of course, you have what we call bandit feedback, which means that only rewards of chosen actions, here treatments, can be observed. If you give here for the two first patients the red treatment, and you observe that they die, okay, you cannot know what would have happened if you give them the blue treatment instead. Okay? This is called bandit feedback. And your goal, of course, is to maximize the cumulative reward up to a certain time horizon. And here, what you want to minimize is to really the number of people you kill, actually, because you don't give them the right treatment. Okay? So it's important. Okay. Is that it's clear for everyone? I guess. Cannot be clear. So usually the performance of algorithms for bandit optimization are measured through the notion of regret, okay, which is equivalent to maximizing average reward up to a certain time. So if you look at these two curves, so the red curves corresponds to the average reward of the best unknown action. You don't know what's the best treatment. So here it would be, let's say, 60%, if the red treatment is better than the blue. Okay. So, and if you knew that the best action, that the best treatment would be the red one, you would always give the red one. Okay. The blue curve is your algorithm. And these curves are instantaneous reward as a function of time. And the notion of regret is just the cumulative losses that the cumulative loss that you have between time zero and time at a certain time t. So the regret is really measuring the rate of convergence of your algorithms towards the optimal action. Okay? Ultimately, of course, you know, law of large numbers, okay, you will be able to learn what's the average success rate of the red and the blue treatments. So if you are not completely stupid, okay, you will have good estimate of these success probabilities. So any non-stupid algorithm should converge to the best treatment. And the notion of regret is telling you how much do I lose on the way, okay? And it's particularly relevant when the best action is evolving over time, right? Because if you have an algorithm that probably minimizes regret, it means that it's converging to the optimal in minimum time with minimum exploration of suboptimal actions, then I hope you believe that it's going to track the best action if the best action is evolving very efficiently. Okay. I'll try to quantify all this in this talk. So the basic stochastic bandit after Thomson was formalized by Robbins in '52. So you have K arms, decisions or actions. So previously it was treatments. They have unknown IID rewards that I denote by XIT for action I at time t, and it's just a Bernoulli distribution for the sake of simplicity here, with average mu I. So the mu I is the probability that the treatment or the action is successful. It gives you a reward 1. You don't know the mu I, of course. That's the bandit looked by Robbins has no structure. It means that mu I belongs to 0, 1. This is the only information that you have, and a priori, there is no relationship between the different mu I. If two treatments, for example, are based on the same molecules, you could have a correlation. And you could try to exploit this correlation to speed up, and to reduce, to speed up the convergence of your algorithm. So an online algorithm is just selecting at a given time an action that depends on all the previously observed arms or decisions. So it depends on the entire history. And the regret up to time t of your algorithm is the difference between the average reward you would have obtained if you knew what was the best decision. This is the performance of an oracle algorithm, minus the reward that you get through your algorithm. Okay. All right. And 33 years later, this problem was solved by probably Lai, I don't know the history, but by solving, when I say solving in this talk, I always say that it means that first, you identify a lower bound on the regret, which means it's identifying a fundamental performance limit that no algorithm can beat. Okay? And the second part of solution is to find an algorithm that reaches this lower bound, which is, of course, an upper bound of the performance. So you find the best algorithm possible. That's what I call we solve the problem. Okay. So Lai and Robbins solved the problem I just mentioned in '95, and the most important result is the derivation of the lower bound, which says that the regret has to scale logarithmically in time, and the constant in front of the logarithm is a sum over all suboptimal actions of their average reward, the difference of the average reward of the best action minus the average reward of this action, divided by a distance between the two corresponding reward distributions. What is important to note is that the regret here is linear in the number of actions, because the sum, as you have one term per action, suboptimal action, and it is proportional to 1 over mu star minus mu I, which is 1 over the difference of reward of the best action and the suboptimal action I. When I started looking at Bandit, this was a bit surprising, because I thought naively that when you have an action that has a reward, average reward that is very close to the optimal, then this is good, because basically it means that, well, if you choose the suboptimal action, it's not a lot of regret. As it turns out, this is the most annoying thing in Bandit optimization. This is the situation where you are going to generate the most amount of regret. And the reason is because you are not able to really distinguish these two actions.
You gain 9 problems.
Sorry?
You gain 9 problems.
You need to probe more to get the information. and much more. And this really this is not balancing the regrets that you have between these two. Anyway, this has to be kept in mind.
You should mention where the name came from.
Which one?
The Bandit.
Bandit. It comes, as far as I know.
The one arm in the end, and K arm, because otherwise people will get a lot of.
All right. So the Bandit term, I think it came from the casino. So basically, if you want to rob a casino, you enter a casino. You have 5 slot machines. You don't know what the probability of winning in these machines, and you try the machine successively. And you want to maximize your reward or minimize the time where your balance is 0, basically. And this is where the terms come from, I think.
It doesn't explain but it does not be able to explain the policy that if you see a machine give a lot of money, you don't go there again for a period of time.
Maybe there is a machine that gives more money.
Now,
That's
if you
the
see
problem.
someone won,
Uh-huh.
and you don't go to that machine for a period of time, you go there. The Bandit doesn't explain.
No. Okay. So the proof of the lower bound is, I won't tell you much, but it's a beautiful argument. It's called the change of measure argument. And basically, here in the x-axis, I put the various actions. You have the best action is I star, is 4. And I'm looking at the number of times action 2, K, must be played by any algorithm. This is how you prove the lower bound. And to compute the minimum number of times the suboptimal arm K must be played, you find a parameter that is the most confusing parameter for your algorithm. Okay? And this parameter is just represented in blue here. You just put the reward of arm K just above the reward of the best action, and you assume that the sample, the history that you receive, is generated by the blue parameter, and you compare with the probability with respect to the red parameter. And this overlapping, overlapping realizations in both under both probability measure under the blue and the red gives you a number of a minimum number of time where the action K must be played, because you cannot distinguish between action K and I star in this overlapping set. In terms of algorithm, of course, you have an optimal algorithm in Lie and Robbins' paper. It was quite complex, and many people tried to really simplify the algorithm. This was achieved by Rajiv Agarwal in '95, a very nice paper. But I guess the most popular scheme today is called UCB. UCB stands for Upper Confidence Bound, and it was derived by Auer and his co-author in 2002. And it's a simple index policy. So it means that you choose the action I that maximize some kind of index, where the index is defined here in the middle of the slide as the empirical average reward that you observe for this action, plus a term that forces you to explore any arm with at least logarithm, a number of times that grows logarithmically over time. Okay, and this in turn actually is another confident bound on your estimator of the average reward of the action. That's why it's called UCB algorithm. UCB algorithm is not optimal. It gives you logarithmic regret. So the regret is growing logarithmically with time, but the constant in front is not correct. Okay. Recently, Garivier and Capet showed that actually you can have a very simple algorithm that's called KL-UCB, based on KL divergence number between your estimate and the best arm, that actually claim back optimality. So you have the right constant and it has logarithmic decay, logarithmic regret. Okay, and the index of an arm of an action I is actually quite simple to compute.
What is the my hat there?
Mu hat is this term here, the empirical average reward of action I. And this algorithm is optimal for a large number of reward distribution, basically reward distributions that are within an exponential family of distribution, like exponential Gaussian, stuff like that. Now, this was the beginning of the story of Bandit optimization in some sense, because this is everything was some kind of trivia, because the problems that I mentioned to you have no structure. So this is how I classify Bandit optimization. There are structured Bandit optimization problems and there are unstructured. So what I talked about is unstructured Bandit. It means that the average reward of different actions are not related to each other. In some sense, it means that a vector of representing the average reward of the various actions belongs to an hyper-rectangle. Okay? By knowing the average reward of action 1, you cannot deduce anything on the average reward of action 2. In problems, in practice, maybe there is connections between mu1 and mu2. This is what I told you when I said maybe the two treatments are made from the same molecules, and as a consequence, the average reward should be correlated. This is what I call structured bandit. So structured bandit is when the vector mu belongs to a set that is not an hyperrectangle. And if it's the case, you should exploit the structural properties, the shape of this set, optimally to reduce your regret. Okay? And the real question is, how can you exploit this structure? It means that if you take an action I, because of the shape of this set, statistically it will give you side information about the other action.
You know the set?
You know the set.
Yeah.
You know the set. And so the question is, how do you optimally exploit this site information, and what will it give you in terms of regret? Okay? And this is crucial because I told you, basically my talk is about Bandit optimization with large strategy sets. Okay? It means that you have a lot of actions. And I told you that if you consider that these actions are unrelated, it's an unstructured bandit, then the regret is going to grow linearly with the number of actions. It's very bad. Okay? If you exploit the structure, you can reduce the dimension, the effective dimension of the problem. Okay. So another way of classifying bandit problem is to look at the ratio between the number of actions divided by the time horizon. Okay? So the Lyon-Robbins framework that I presented earlier is a problem where basically the time tends to infinity and the number of actions remain finite. So this is a scenario, and most of the scenarios are there is when this ratio is 0. Okay? On the other side of the spectrum, you have what we call infinite bandit problems. It's a Chinese restaurant problem in New York. You go to New York, maybe you will go 100 times in your life to a Chinese restaurant in New York. There are 10,000 Chinese restaurants in New York. So there are many more actions than actually what you can explore. So what do you do in this case? So this problem was investigated by Berry in the 90s, and they made mistakes in their analysis. And we recently solved the problem with Professor Bonald from Telecom R&D, and it's appearing this year at NIPS, if you are interested. It's not simple. In the middle of the spectrum, you have what I call bandit with structure, where basically the number of actions can be quite large, but actually by exploiting the structure, you will manage to do as if the ratio between number of actions and time horizon tends to 0. Okay. And so you have, of course, interesting work, previous work on Bandit with structure. You have when the structure is linear, when it is convex, and what I'm going to solve today is a unimodal structure. Okay.
Convexity is the set theta.
Convexity means that the reward is a convex function of some parameters. You can put your action so that the reward is a convex function of the actions. Okay. So it is a very interesting topic nowadays, bandit optimization. This is a slide I took from ICML tutorial by Oliver and Munoz. It's a huge number of papers. Every week you have 5 more. It's very difficult to follow up. It attracts a lot of people from machine learning, and I think the popularity of bandit optimization today is due to the fact that it has many applications in the online world, like e-commerce, like the second motivation I discussed earlier in my talk. In lotteries, I mean, this would be an infinite bandit problem. All right. So the technical contribution here is to solve graphical unimodal bandits. Okay. So what are graphically unimodal bandits? They were introduced by Yu and Manor, Manor in 2011 in an ICML paper, and it's an important class of structure because it's very natural. So in unimodal bandit, you have a graph where the vertices of these graphs corresponds to your actions, and the edge of the graphs corresponds to relationships or a relation between the corresponding average reward. And it's graphically unimodal if when I put the best action K star from any suboptimal action, there is a path leading to K star to the best vertex, such that along the way you are going to increase your average reward. Okay? It means that if you were smart enough and apply some kind of gradient algorithm, you would find the best action. Okay? It's unimodal. Of course, one particular case is when the graph is aligned and you have really unimodality. Okay?
So you want monotonicity along the path.
There is a path from any suboptimal action to the best action along which you are going to increase.
It's not just that it is a path to the optimal, but you want the path to be monotonically improving.
Yeah,
there is a path with increasing reward. Yes, if you want.
And is it clear that there are non-trivial structures?
Of course, yeah. What do you mean?
Well, but if I have to, you said for every node, right? To any other node, right? There is.
No, not to any other node. To the one. So it's a graph, and you put the average reward on top of it, okay? And you ask yourself, okay, can I go from a suboptimal point to the point where there is the best reward? Okay.
And that reward is unique. Or?
Here it's unique. Yes. It's unimodal. Okay. It's
no,
really.
All right. But are there problems where this is the case and it's not really straight line that you mentioned?
Of course. This is. I mean.
No, I'm asking because
Yeah.
all the other things are things on the empty set. Right?
Yeah. No, it's not. Of course, it's not the empty set. So think of it. I mean, what would you do if you don't know the structure? You don't know the graph. If you I give you any vector mu. If you put the complete graph, this is unimodal. Okay. Of course, it doesn't give you anything. But what you are going to do is you start with a complete graph, and you are starting pruning the graph so that it becomes as sparse as possible, but still maintains this unimodal structure. Okay? The unimodal structure is there naturally in many problems, in economics, this is used in pricing and stuff, and my application is a bit
What is the anti-relationship?
relationship. It means that the average reward of one action is related to the average reward of another action. It means bigger reward or smaller reward. It's a partial order.
So the relationship whether it's bigger or smaller.
Exactly. So basically,
And how do you designate whether it's bigger or smaller? Is there a sign on them?
no. So this is a node. This is an action.
Right.
This is another action. If there is a link here,
Yeah.
maybe if this link belongs to one path towards the optimal arm, then I assume that the average reward here is bigger than this one. This is the relationship between the two nodes.
Alex?
Not the other way around. So the graph is directed.
It's not directed, but you could direct it.
So when
There is a path. It could be a path with undirected or directed.
So if you have a real problem, would this graph given to you, or is it something you need to
That's
construct?
a good question. So as I answered Armand earlier, if you don't know, what you are going to do is that you start with a complete graph, and then maybe you run a stupid Bandit algorithm out of in the literature, and you look where the algorithm is going.
But if you are thinking of a pruning, in order to actually ensure that you have a unimodal graph, you have to kind of know the relation that you said, but you need to know the partial order at least. But that means you need to have additional information.
Yes. So in some of the problems, the structure comes for free because you have models. Okay, this is the case in AO 2.11. You know that it's unimodal. You have models that explains why it should be unimodal, because each action corresponds to a modulation encoding schemes for which you have models of the success probability and so on, and you know that it is unimodal. When you don't know it, that's what I think you have to run pre-experiments to actually find out the graph. But this is what we did when we selected the rate and the MIMO mode. We run a lot of experiments to just find out what is the graph. And to be sure that we have the right graph, I mean, you put extra edges just to be sure. Okay.
So the graph a secret then?
Sorry?
The graph is a secret or not?
It doesn't matter if it's acyclic or not. What matters, the definition is here. From any vertex, there is a path that goes to the best vertex with increasing reward. It cannot be, I mean, you cannot have cycles.
You're right. So it's a secret then.
So,
Right? I mean, you cannot have cycles, right? Because otherwise you would have new.
the path toward the set of paths leading to K star, the best, of course, is a spanning tree, right?
Right.
But it's acyclic.
Okay.
But the graph is it can have cycles.
Alright.
Look at all the triangles I have
This
here.
property is testable.
Now you.
This property is testable.
Sorry.
This property is testable.
So this property again, it should be tested before you run your
This is
algorithm.
testable.
What do you mean testable?
Can you detect the problem first, the property or not?
Yeah, I mean if you by yeah, maybe it's okay. Can you precise the definition of testing?
I have a Bandit problem.
Yes.
And I'm trying to find if I can categorize it as a new model.
Okay.
I have to discover now the graph relationship with this property. So is it possible to design experiment to do it or not?
So this
Or is there something else that's in
I never asked myself this question, but yeah, this is something we would like to do, but along the same line as my answer to Armand. I mean, you start with complete graph, and you have an algorithm that basically is some kind of gradient, and you look at if you find the way or not. But it's very difficult to answer this question.
Can I ask you one more question?
Yes.
Do you have some idea as to how quickly the size of the edges that increases with the number of vertices in this graph? to make sure that you end up with a unimodal graph?
Well, it depends pretty much on your problem, right? It depends on the mu,
Right.
the vector mu. So I mean,
For the
it can be
problems that you
anything.
looked at?
The worst case is complete graph, and it means that you have no relationship whatsoever. You have no partial order in the mu. And the best case, maybe it's the line. So you see what I mean?
Yeah, okay.
It's from degree n to degree 2. So it's very difficult to answer this question again. But your goal as a designer is to exploit your a priori knowledge of the problem to design the minimum graph, right?
Right.
Because the algorithm is going to converge as fast as possible there.
Okay, can you define, if I wanted to define the program, and whether a Bandit program structure is remote,
Yeah.
what I would give?
To define unimodality?
No. I don't have a Bandit program. I
Yeah.
know the relationship theta set that we said before.
Mhm.
I know precisely the theta set,
Yeah.
the relationship. And I want to test if this Bandit program is unimodal. What do I have to have to be able to do that?
Yeah, I mean, you have to find a partial order.
You have to find
so,
a partial
so let's see.
What are you
Here.
giving? What you have to
So
find?
I give you this set theta, okay, and what you are asking is, okay, for any point in this theta, can I find a partial order? Okay, that corresponds to a graph, and basically, what you will do. So for each point, you find a graph, okay, that satisfies unimodality, and then what you need is to take the union of all these graphs. If you want the problem to be unimodal for any u within this theta. Okay?
Does that then require that the moon that you have be look differently than?
Oh, I didn't say the moon was unimodal.
No, but likely to be convex, no? Or have some convexity property, no?
Yeah, it's a good question. I never thought about
I mean,
this.
it's-
Yeah,
Go on.
yeah.
Well, it depends on the payoff function as well.
Yeah. Okay, so let's move on a little bit. So, so here is what we assume. I mean, it's a bit more than unimodality, but this is well. I mean, you understand that unimodality is one thing. We have a bit more of structure here, but it's not crucial. This is just for the sake of the application. So you have, the problem I'm considering is that you have an action I. It has a reward Ri times a random variable xit that is a Bernoulli distribution with success probability theta I. So this is exactly the rate adaptation problems that I had earlier. Okay, this is why I introduced this Ri, which are the rates. And the average reward are just the product of Ri and theta I. You don't know theta I, you don't know mu I. And you have graphical unimodality with respect to some graph G that you know. Okay. Now, what can you do? That's the question. What can you do in terms of regret? And how do you exploit optimally this structure? Okay. And how this optimal regret will depend on the size of the graph, the structure, and so on. Okay. And so to answer this question, we went back to the 90s and looked at all the work by Kumar, Lai, Burka, all these big names in stochastic control. And in these guys, they looked at much more general systems that are basically controlled Markov chain with unknown parameters. I won't get into the detail because, wow, it's very late. But please come to me after the talk if you want to see the bridge between the two fields. Okay. And actually, what you can show is that for this kind of control Markov chain with unknown parameters, you are able to also find the lower bound of the regret. So the regret that cannot be beaten by any algorithm. Okay? And if you apply this to our problem, which is not so trivial. Yes, please.
Can you go to the formula?
Yes. This one?
Yeah. So the divergence comes because you try to estimate the thing.
Yes, so basically,
So you use separator somewhere?
so yeah, there is no separation assumed here. Okay, so this
You don't
number,
have to assume you are a Markov chain.
it's a Markov chain.
So the information state is the condition of probability.
Okay, the state of the Markov chain is whatever you like. Okay. In our Bandit problem, we don't need really the state. The state is only giving you the reward that you obtained in the previous
I
action.
understand, but I'm saying if I apply general stress control problem to this, right, and I have a known parameters, right? General separation of stress control says I will fulfill the condition of distribution of the parameters,
Yes.
and then the control is a function of the parameters. Is that the reason why the KL comes there? You know, I mean,
Maybe,
you
but
have to
this is more complex than that in the Bandit setting, because you have to, there is the main problem is to ensure that you have what they call certainty equivalence. That
you don't need that. Okay?
you need that here.
Let me explain.
Yeah.
In general stochastic control problem, there is a general exact separation theorem in the book of Variety and Kumar. It says that the control is a numberless function of the information state. And then you have to find the information state. In Markov chain, the information state is usually a conditional distribution function which you can actually write equation about.
Well,
The question is whether that reduces, in this case, because they are known here the parameters. And the trick to do is we reduce states that spare the parameters. Right? We write equations which give the parameters nu n plus 1 equals to n, and that's unknown. Is that why it comes to or not?
maybe I didn't really look at this way, but
KL comes from the mismatch.
But it will come to also. Because the KL comes very much related to the problem. Anyway, I mean,
But, I mean,
if you're right, then I think were you to specialize to your earlier results, you should find it.
yeah, that's it.
And I don't know if that has been done or not.
no, I mean it's
But in
very
your papers, you have the passage from stress control in this problem?
yes. So you can, but it's a very specific paper from stochastic control. It's not classical stuff. So the main contribution is by Graves and Lai in '97. It's an amazing paper because it's so general, and it was cited only 20 times, and it's it's really a mess because all the papers on bandit optimization should know about this. Okay. And they reinvent the wheel a lot of times, but these guys they did it earlier, and in a much more general framework.
You know this theorem, right? The number of citations in the paper are inversely proportional to significance in the paper.
Well, I mean, I'm not sure it's always true.
I mean, I didn't say that. I'm not saying it.
I wrote a lot of patch papers with small number of citations.
You are in the table.
I'm saying, right?
You are in the table of this indistinguishability in these papers.
Anyway, so yes, so when you apply this theory and you adapt it a little bit, you find out that actually in unimodal bandit, the only thing that matters is the local structure close to the optimal action in the graph.
Local means one hop away.
Yes, one hop away. So the regret is going to scale logarithmically with time, and the constant is just the sum over the neighbors or some neighbors of the optimal action.
All or some?
Some of them, because here I introduce a array RK that multiplies all the rewards. And so there are actions in the neighborhood that you don't need to explore because their rate is that small that you know already that they are going to be very bad, not suboptimal. So it's very good news because in unimodal bandit, and this is what we prove, the performance limit does not depend on the size of the graph. It's only depends on the maximal degree of the graph. And the proof is again some kind of change of measure, and I won't discuss this. So now the real challenge is to find something that you can implement and that reach this optimal performance. And this algorithm that we found is called optimal action sampling. Okay, is based on the empirical rewards you observe for the various actions. It's it is defined through the notion of leader, which is the leader at time n is the action that gave you the best reward so far. And it's also based on the number of times the various actions have been the leader during your at a given time. And the algorithm is based on an index that looks like KL-UCB index, okay? But it's not an index policy. Why is it not an index policy, the optimal algorithm? Because there is structure. So an index policy can only be optimal in unstructured bandit, okay? Here, because you have structure, you don't have indexability of the optimal strategy, okay? So you have an index, but yes.
So the index of K, and that's what KN, right?
Yes.
So what is N here?
N is time, is number of steps.
Right. And that's the minus. But that gives you an order of all the K, right?
Sorry?
That gives you an order of all
That gives you an order,
Yeah.
but the algorithm is actually more or less choosing the action that is the neighbor of the leader at some time, and that maximize the index. So basically you look at a restricted set of actions each time, and you take the one with the maximal index. So it's not an index policy.
So the BKN doesn't tell you.
No, it doesn't tell you, because you have to look at where the leader is, and you look at his neighbor. And so you can show that this algorithm is actually reaching is optimal. Okay? It's not. So the proof is, as usually in this field, it's a smart decomposition of the sample path of the problem. It's used concentration inequalities. Here we derived a new one that was it's actually quite cute. And what is nice with the analysis we made is that we have finite time analysis. So it means that it's not asymptotic over time. It's for all time we have a bound on regret. Okay.
How does it go?
Huh?
How does it go with all the time?
So you have the logarithmic term and the right constant, and you have a row of log t terms that are next. Okay, and we know what are these terms.
You know the point?
Yeah, we know everything. We know actually the third term. Okay, it's details. So to answer your question, what about non-stationary environment? Actually, as an engineer, I am interested in cases where things are evolving over time. What I want to do is to track the best action over time. Okay. So here the theta parameter, it's a vector, or the mu if you want, is evolving over time. The best action K star is evolving over time. You don't know it. And of course, your goal is to track the best decision, so you have to modify your notion of regret. Okay? Now your regret at time t is the difference between the average reward of an oracle algorithm that knows which one is the best action at all time and the performance of your algorithm. So it's really trying to, if you were able to know, to track the best decision, this would give a regret equal to 0. Okay? It was shown that if you have some not stupid assumption on the way theta is evolving, it's impossible to have sublinear regret. Okay? It's very natural and intuitive. Most of the work in non-stationary bandits were a bit cheating, because they assume that you always have a separation of the reward of the arms. It means that the theta function is a jumping process, if you want, okay? It means that you have suddenly a big change in theta, so that action 1 was optimal, and then suddenly action 2 is optimal, and the separation is lower bounded by something strictly positive. And if you remember Graves and Lie lower bound, you remember that the problem is really when things are crossing each other. Because when things are close to each other, it's very difficult to know which one is the best, and this will generate a lot of regret. Okay? And this is what we did. We are, I think, the first to do, to assume that theta of t is just a Lipschitz function with some parameter c. And the regret bound that we get is of our algorithm is, let's say, a function of the time arms are crossing each other. This is this phi k of delta that I denoted here. K is number of actions. So if you take our algorithm for stationary scenario, if you put a sliding window, so basically it means that your decision at time t depends on your history only in the interval t minus tau t, then you can show that if you know the sigma, if you know the way roughly theta is evolving, if you choose your window size accordingly, but this is the formula, okay, then you have a regret, a linear regret, for which you can bound the constant. And the constant, what is very important here, it tends to 0 when sigma tends to 0. So it means that when the evolution of the theta is slower and slower, your algorithm is better and better. Okay? It's okay. You can. This is what you.
What's the window size again here? Tau.
Tau. Yes. Okay. So. Blah, blah, blah.
That's assuming that you know that sigma, right?
You know that sigma, yes. That's a good question. Okay, so if you apply that to rate adaptation, of course you understand that this was an unimodal problem. When you have, when you just choose the rate, this is just an unimodal Bandit problem in one dimension. The graph is a line, okay? In addition to unimodality, we have some information about the thetas. We know that if you transmit at a lower rate, the success probability is higher than if you transmit at a higher rate. So you have an additional structure that you can actually exploit, okay? And we can do that, okay? In the MIMO case, so this is this graph G that we found the most relevant was this one. It was done experimentally. So I have to say that this work is a collaboration with people in KAIST. They have a fantastic test bed there. And we use that to experiment a lot our algorithm. And in MIMO systems, we have found out that there is a natural graph that provides unimodality all the time. So, okay, in all scenario, in all possible, you want your algorithms to work all the time. In all scenario, indoor, outdoor, and so on. So, just intuitively how to explain this graph. So DS refers to the dual mode. It means that you send different information through the two antennas. Single stream, SS mode, means that you send a single packet through the two antennas. When you transmit at lower rate, the single stream mode is always optimal. Okay? It means that basically the receiver is very far. And in this case, we found that dual mode is always suboptimal. This is why these actions are not even part of the graph. Okay? Symmetrically, when the rate is very high, a single stream mode is suboptimal. Okay? If you are very close to the base station, to the access point, you want to use all antennas. And in the middle, we don't know much. That's why we put all these edges. Okay?
It's a full graph.
Inside, it's not a full graph, but yes. It's not a full graph. You don't jump from here to here without passing through here. Okay, if you look at it for 5 minutes, you'll see that it's pretty much reasonable. Okay.
And this was massive.
This is experimentally designed.
Now, why don't you have a line from 54 to 162? What is that?
From?
I understand what you're saying. Why don't I have also a line in 54 to 162?
Okay, because think of it. I mean, if you're not able to send a single packet at a rate 52 megabits per second using a single mode,
Right.
sending a packet at 108 is double rate, okay? So it means that you would be able to send a packet at rate, let's say, 54 megabit through two antennas simultaneously.
Okay.
But you are not able to do it in single mode. So even this line is a bit fishy. You understand?
That's double.
Huh?
182 times 54. So
Yes. So what I'm saying is that
162 is more than that.
if you have a failure here, it's very likely that you have a failure here.
Right.
Because here you use two antennas for the same thing, and here you use one antenna, here two antennas. So that's why we don't have a link here, because I mean,
you're saying if I go to higher rate,
it's gonna fail. I mean,
The
we
failure
don't need.
isn't there also a kind of a order constraint that comes from the fact that you have this line cost area greater than uj, therefore you cannot have it.
Yeah, it's so first of all, yeah, there is unimodality per MIMO mode.
Sure.
And then after that you have to arrange a little bit because things are not unimodal just looking at the rates. But I mean,
And the arrow goes which way?
there is no arrow. When we put a link between two nodes, it means that this one could be better than this one, but there are scenarios where this one is better than this one. Okay?
And how does that jive to what you said earlier, where you said for every chase star can find the path,
This graph does not include the representation of the average reward. I'm telling you that for the theta set, the moon set that I had, if I put a mu there, it's going to be unimodal with respect to this graph. Whatever the mu I take from this moon. Okay? You see what I mean? Okay, so rate adaptation, lot of state of the art. We are using auto rate fallback, a very suboptimal algorithm. One of the state-of-the-art algorithm was known as sample rate. It was designed in MIT by a student, and they are all heuristic, like all the communication protocols in the internet, by the way. Okay. And so what we claim back is that we designed the optimal algorithm. Okay. And as you see, the performance is spectacularly better with our algorithm. This is just a representation of regret as function of time for AO2.11j, and we tested different kind of scenarios that correspond to different radio environment. And always we found that even sample rate, that is supposed to be much better than ARF, is really bad. Okay? And in non-stationary environment, we have also experiments. So here we moved with the computer in the lab, okay? And the best rate, these are traces, okay? This is not the performance. This is the throughput you would observe by choosing the various actions. So you see that at time 0, the best action is to transmit at 54 megabits per second, but after time 30 seconds or something, the red, which is 36, is better. Okay? And this is the result of our algorithm versus the Oracle algorithm and sample rate algorithm. And we track quite well the best action. Okay? This is a scenario where fading is quite slow. So basically, in the indoor environment, when people move, generally the slow fading component, well, the shadowing component, let's say, of the fading is moving quite slowly, and this is why we are able to track it. The problem will be less difficult in the future, because in the future we will move at the same speed, but we will send at rates that are much bigger. We always increase the rate at which we send, which means that to send one packet, it takes less and less time, which means in terms that you have more and more information and more feedback from the system. Okay? And to summarize, I hope to convince you that regret minimization is the right objective for tracking optimal operating points in the system in a changing environment. And we gave the first, I think, complete solution to a structured bandit problem. We have lower bound, we have an optimal algorithm, we have non-stationary and finite time analysis of the algorithm. And it has spectacular application in my point of view. I'm looking at the second example I described in the initial part of my talk, now the online matrix completion problem. If you remember, it's a much more difficult problem because this is a problem when the structure you don't know about it. Okay? You know there is a structure, maybe the matrix of the click-through rate is of low rank, but you don't know which structure it has. And so the problem has an additional learning part where you have to learn where is the structure. And this is much more challenging and very interesting, actually. And in general, the Bandit problems that are not solved are Bandit problems that are in the middle of my classification. Bandit's problems where, let's say, you have an horizon of time t, and you have a number of arms, square root of t, or t to the power something. And this scales to infinity. So the number of action is not either huge compared to the time horizon, nor 0. So what do you do in this case? I think this is very interesting area of research, maybe very difficult as well. And I will stop here. And you can visit Richard's webpage or my webpage for more information and papers. Thank you very much.
Thank you. Questions?
So the performance bound that you had in the static case, it depended on the local structure around the optimal vortex.
Right.
But the graph that you're using is the one that you constructed. Presumably it's a minimal unimodal graph. But is it clear that in fact there is a unique one that will give you the minimum value? And how do you find it?
That's a very good question.
You don't need to use it.
Yeah. So in some sense, I have a contradiction because I say, oh, I have the lower bound, but then are you sure that the graph is actually the minimum graph? Right. So that's a very good question. So let me think.
Do you need that it be?
You don't need to use the graph.
Okay.
Because
So,
you use to construct a graph.
yeah. I have the answer. Sorry, it took me a while, but okay. So the lower bound is derived, is valid for any mu within the moon. Okay. The moon has some graph and that are minima. Okay. So basically, the lower bound that I have is a lower bound that is satisfied by any what's called uniformly good algorithm. Uniformly good algorithms are algorithms that for any mu within the moon is going to test suboptimal action at most logarithmic number of times as time goes on. So this is a connection. Okay. For all algorithms that are uniformly good when the parameter is in the mood, then you have this lower bound. And this basically make a connection between answer your question.
So if I don't have a unique model graph,
You need to take the union if you want to
do I
treat
get a better algorithm? Is there any comparison on the resulting strategy based on the graphs themselves?
Yeah, exactly.
So that's a question.
No, there is no comparison, and you can compare. This is somehow what you want to do in your routing problem. Yes. So
Any relations to monotropic optimization?
maybe there is always a relation
No, but
with
it's
everything.
It's almost a definition, okay, in this setup. Because you want to go from one node to the other, potentially increasing them.
Right. I think monotropic optimization framework has more structure, even more structure than this one.
Listen. Now, another question. So what is the meaning of the graph?
The graph means
Because I understand what the nodes are.
mhm,
And the links mean?
the links means for any mu within the moon, for any you have. So what you start with is a
Where do I
knowledge.
draw a link? I mean, I have graph. I have, as you said in the demo thing, right? I have the nodes. I understand what the nodes are. When do I draw a link?
Exactly.
What
So
do I
good question.
semantically mean by that?
So you draw a link between two actions when these two actions, when there exists a mu in the moon, this is your a priori knowledge about the problem. You know that the probability of success are, for example, if you have two rates, it's theta 1, theta 2, you know that theta 1 is bigger than theta 2, so it would be a triangle. This is your moon. So you draw an edge between two nodes if you know, if there exists a mu, such that this link is used within an increasing reward path towards the best action. That's the definition of your graph.
But now you're using a path to define a link, and that's very unhelpful.
I mean,
Right? And we'll go the other way, right? Anyway, we'll
okay, maybe there is a definition. So,
Okay. Any other questions? Right, thank you very much.
thank you.